Now, the overall idea here was we were going to build some sort of robotic automated machine that would go out, pick up some trash, and once it picks up trash, it'd bring it into a home area. Communicate with some sort of circuitry that would say, all right, hey, I got a piece of trash. Where can I put this? And the circuitry would go, oh, you can put it over here. And then they'd be, oh, okay, so where are you? Where are you? Oh, there you are. And I'll head that direction. And so we came up with this robot. It started out with just building a regular chassis. Then from there, we're like, oh, let's make sure that it doesn't run into any walls. So let's add some autonomous programming in there. Oh, let's make sure it knows when it has a piece of trash. So we decided whether or not we wanted to use a push button or an ultrasound sensor. We gravitate more towards the ultrasound sensor, but we still kept the code for the push button. And how are we going to get this trash? Well, we developed a little claw that will come down and it'll trap it and make sure that it's there. And so here's the robot in action. We have the robot's claw up. And you can see it's all folded up there. And then once it gets deployed, it's trapped in the garbage. It's not getting out. Now here's our desired circuit. Now if you look at the top part of this figure that I have, we have this microphone signal that's going in. We're looking mainly at a sine signal between 400 hertz and 440 hertz. I added about 20 hertz deviation there just in case the Lego Mindstorm wasn't emitting it right. It wasn't picking up the right signal, whatever. So we're just sending that into a non-inverting amplifier. We're sending that into an op amp. And then from there, we're sending that into a full wave rectifier. So we'll just see a whole bunch of these bumps, upward bumps. And then the diodes would start flashing because they're like, oh, yes, I see that signal and I am going to emit a flash correspondingly. And so then if you look at the bottom part of the figure, we have the defective protocol. So it's just a standard voltage divider where in the second half we have this potentiometer, and based on the different resistance of that potentiometer, we're going to have a turn to the left or a turn to the right. And if you look at the far left side, we have a diode circuit. So the diode circuit, that's when the lab jack processes, yes, I heard the 440 signal, I'm going to emit a diode saying, yes, I heard this so Walle can find his way home. And so here's the real circuit, and I'll let Catherine Combs talk about this for a little bit.
This circuit, which just lights this LED, and that's when Walle will know when to head back.
Take over. Alright, now that we have that fantastic description from Katie, let's talk a little bit about the code. This is the part that me personally, Jacob, am really excited about, is developing the nice interface between the person and the electronics, getting them to talk in some certain way. Now, the hardest part, it really seemed, was getting the right signal out of the mic. And I don't know why, but we were actually having a bunch of problems with this microphone. And getting that signal, go through the amplifier, and then once it's going out the amplifier, make sure that it's emitting at the right voltage. It just seemed like there was a lot of pain here. So we developed a really nice lab view code to kind of help us guide us along. Now here's the interface. We have about two distinct sections. We have what's being outputted by the circuit and what we want to look for in the circuit. If we look over here in the left side, we can see that we can choose whether or not we're using the push button. Now this was kind of important because if we were using the push button, we probably weren't going to use the ultrasound. If we were using ultrasound for the trash detection, we did not want to use the push button. So we made this button selection. Looking for the mic signal. We want to make sure that we were getting the right thing, so we turned off everything else and just looked at the mic signal. Now, the defective protocol, we don't always want to have the defective protocol going, so we made it this push button. We want to turn on the Walle bot every now and then, too. And so we have the mic signal right here, and the mic signal is kind of cool. It's up and downs. We have the fast Fourier transform to make sure we're getting the right signs. And if you look down here on the x-axis of that, we actually aren't getting the right ones, so we're still in the process of figuring that out. Now, the filtered signal, I happened to take the snapshot when it wasn't filled up all the way. The way that my specific filter works is that it takes an array of values, and then it looks at it saying, oh, is it within this deviation? Oh, okay, yeah, for these past 100 values or so, it's working. And so we also get to see if the push button's pressed, if the Mindstorm is singing or not, what is the voltage drop across the microphone, make sure the graph's not lying to us, how far are we from the wall, and all this other stuff right here. And we can actually see the error output, and what kind of color is detected, make sure it's actually seeing the LED on the LED board. And so here's the part for getting the mic signal. Now here's this. Now it's not that real difficult. It's just a whole bunch of LabVIEW. In all honesty, what we have here is we're taking an input right here. We're graphing it. Now we're going to see what that voltage is at that point. Now we're going to build an array, send it through a fast Fourier transform. We're going to graph that. Now we're going to take that array before the fast Fourier transform, this raw data array of data. We're going to shove that through a low-pass filter. I believe I used the Butterworth filter right here. We use the Butterworth filter, and we're going to actually graph that filtered signal. Then once we're going to see that, we're going to do another bandpass filter. And if this is true, then we're going to put a little voltage across a diode. Now, this is all fun. Now, let's go to the defective protocol. Now, the defective protocol pretty much just works off that standard voltage divider equation. It looks at the voltage drop across the second resistor, or potentiometer in this case, and it actuates the different power to each motor based on that voltage drop. And we have that right here. If the voltage drop is not equal to 2.5, because I had about 5 volts coming in, then let's do this. And it weights based on the input. Now, here's the autonomous code. We're looking at if we're using the push button or not. If not, like in most cases, we're actually just using the ultrasonic sensor right here. And if it's less than 20 centimeters, let's start singing. So it's not all that interesting. It's really just a bunch of notes, but if you're curious, here's pieces of the notes. I didn't include the entire code for this section because the majority is just it singing La Cucaracha. And here's that. Here's the end of the song, right over here. And here's the color detection. If the color is red, then stop this, go to the next part of the sequence. And if it's red again, make sure that you're seeing the right thing. Brake, and run towards it. Go home, and make sure that it's there. Now that I've kind of shown you what kind of code we've been using so far, I really want to show you how these robots actually act out in the field. So, So, as I said in the video, we have these 3 screens. We have the mic signal, the raw mic signal right here. We have the filtered signal. It's going to get there. What's happening is it's creating this giant array right now, and it's going to cycle through them, making sure that they are actually within the certain bandwidth that I put. I think I put 500 to 300 hertz. And here we actually have the fast Fourier transform of that signal right there. And so this is going to create essentially a histogram of the number of hertz that it sees throughout the entire signal. Now, wasn't that cool? Well, let's kind of talk over the things that we've learned so far, at least as us, as a team, me and Catherine. So going through all this drudgery and doing all this work, we've kind of learned how to actually read the data sheets. As simple of a task as that seems, it was actually a big offset. It was surprisingly really difficult for us to actually get a handle, okay, which pinout goes to where, and do these actually line up with the schematics that we saw in those MEMS books. And making sure that our V outs from the power supply were actually negative and positive Vs, like we would want to put into the op amp. And making sure that elements are getting what they need, just measuring it. Just take a test probe and measuring it. Is this what we actually want? Instead of just running it saying, oh, well, we messed up here, I guess we're done. Actually making sure that each part, each element is getting the voltage that it actually needed. So the problems that I solved, well, we didn't have a lot of things that really worked well or really worked. So the actual problem that we actually ended up solving was really just developing some sort of LED and noise-based protocol that could communicate between the Mindstorm and the lab jack so that they knew what the other one was doing at all times and how they could actually improve upon themselves so that the other one might actually be able to make it home, get some repairs, and actually do its job. So as a quick summary, I know these actual drawings don't really match up with everything that I've talked about, but here we have the autopilot and the defective summary of what's going on. So if we look at the one on the left, the AV3 gets some trash, and so it emits some sort of 400 hertz sound, 440 sound. It sends it to a microphone. The microphone gets amplified somehow, and it sends it to a frequency selector in the lab view and the lab jack. And then we watch that voltage drop across an LED. And the lab jack sends it to another LED saying, yes, we got that signal. And then that sends it back to the EV3 to see what's your status. And then if we go to the right on the defective protocol, we have measured the voltage drop across just a standard voltage divider. And we use the potentiometer to vary the different voltages across that potentiometer. And we articulate the robot based on that voltage drop. And brings the trash home. If it has any, make sure that it gets any repairs, and it goes upon its way, goes back into autopilot mode. Alright, well, I hope you enjoyed this presentation, and have a nice day.